For billions of years, Earth has quietly traveled through a dangerous neighborhood of space. Around the Sun, millions of rocky fragments continue their endless journey. Silent survivors left behind after the solar system was born nearly 4.6 billion years ago. Most will never come anywhere near our planet, but a small number follow unstable paths, slowly reshaped by gravity over millions of years until one day, they cross Earth's orbit. Unlike the disasters we experience on Earth, an asteroid gives no warning sirens, no towering storm clouds, and no shaking ground before its arrival. In the vacuum of space, it races through complete silence. It doesn't produce its own light. It carries no engine, no fire, and no intention. It is simply a piece of ancient rock following the unbreakable laws of physics. From the surface of Earth, these objects are incredibly difficult to see. Many are darker than coal, reflecting only a tiny fraction of the sunlight that reaches them. Unless the geometry is just right, even a large asteroid can remain almost invisible against the blackness of space. By the time it becomes bright enough to detect, the clock may already be ticking. This isn't the plot of a science fiction movie. Planetary defense is a real scientific field, and astronomers spend every night scanning the skies for objects that could one day threaten our world. But that raises an unsettling question. If a dangerous asteroid were discovered heading toward Earth, would humanity actually be able to stop it? Chapter 1: The Origins of Asteroids and Comets. Long before Earth became a world filled with oceans, forests, and life, our solar system was nothing more than an enormous cloud of gas and microscopic dust drifting through space. Around 4.6 billion years ago, gravity slowly pulled this material together, giving birth to the young sun. As it grew brighter, the remaining dust began colliding, sticking together, and forming countless rocky bodies known as planetesimals, the first building blocks of the planets. Over millions of years, many of these objects merged through repeated collisions, eventually becoming the worlds we recognize today. But not every fragment found a place in a planet. Millions of rocky leftovers survived this chaotic era, continuing to orbit the sun as ancient relics from the solar system's formation. These surviving fragments are what we now call asteroids. Rather than floating randomly through space, asteroids follow predictable paths governed by gravity. Most are concentrated in the asteroid belt between Mars and Jupiter, where countless objects have remained in orbit for billions of years. Yet this region is far from peaceful. Every asteroid is constantly influenced by the gravitational pull of the sun and the planets, especially Jupiter, the giant of our solar system. Although many asteroids will never leave their distant orbits, gravity is always at work. Over immense periods of time, even tiny changes can gradually reshape an asteroid's path. A rock that has traveled harmlessly for billions of years can slowly begin a journey that brings it closer and closer to Earth. But how can a planet as small as ours ever cross paths with a rock that began its journey billions of years ago? Yet the story doesn't end with the birth of these ancient worlds. Although millions of asteroids have remained in stable orbits for billions of years, the solar system is far from static. It is a constantly evolving gravitational system where even the smallest changes, given enough time, can completely alter an object's future. Among all the planets, Jupiter exerts the greatest influence. As the most massive planet in our solar system, its immense gravity subtly reshapes the orbits of nearby asteroids. Some drift into regions known as orbital resonances, where Jupiter's repeated gravitational pull acts like a perfectly timed series of gentle pushes. Individually, these nudges are almost insignificant, but over millions of years, they gradually stretch an asteroid's orbit, sending it farther from the main belt. Even sunlight plays an unexpected role. Every asteroid absorbs energy from the sun and slowly releases that heat back into space. This tiny imbalance creates an incredibly weak force called the Yarkovsky effect. Although impossible to notice over days or even centuries, its influence accumulates over millions of years, shifting an asteroid's orbit just enough to place it on an entirely different path. Once these ancient rocks escape the asteroid belt, they begin wandering through the inner solar system, crossing the paths of Mars, Earth, and the other terrestrial planets. Most continue their journey without incident, passing harmlessly through space. But a small number enter orbits that bring them repeatedly close to Earth. From that moment, they are no longer just ancient remnants of the solar system. They become something scientists watch with extraordinary attention: near-Earth objects. And understanding them may one day determine humanity's ability to prevent a future catastrophe. Chapter 2: When a space rock becomes a threat. By the time an asteroid reaches Earth's neighborhood, it has already completed a journey lasting billions of years. Yet its presence alone does not mean our planet is in danger. Space is unimaginably vast, and even objects whose orbits cross Earth's path usually pass at enormous distances. Every year, countless asteroids make close approaches without posing any immediate threat. So how do scientists decide which objects deserve serious attention? The answer begins with careful observation. As soon as a new asteroid is discovered, astronomers around the world repeatedly track its position against the background stars. Each observation refines its orbit, allowing computers to calculate where the asteroid will travel not only tomorrow, but decades or even centuries into the future. This process transforms a faint moving point of light into a predictable celestial object. Not every newly discovered asteroid follows a perfectly known path. During the first days or weeks after discovery, limited observations leave room for uncertainty. Instead of predicting one exact orbit, scientists calculate a range of possible trajectories based on the available data. As additional observations are collected, that range steadily narrows, revealing whether the asteroid will safely miss Earth or requires closer monitoring. Only a very small fraction continue to demand attention. These objects are known as near-Earth objects, or NEOs, asteroids and comets whose orbits bring them into Earth's cosmic neighborhood. Most will never strike our planet, but among thousands of known NEOs, a much smaller group is monitored with extraordinary care because even a tiny uncertainty in their future path could have enormous consequences. So what separates an ordinary near-Earth object from one capable of triggering a global planetary defense response? Discovering a near-Earth object is only the beginning. The far greater challenge is determining whether it could ever collide with Earth. That calculation depends on far more than simply drawing two lines across a map of the solar system. Every planet is moving. Every asteroid is moving, and each follows its own orbit around the Sun. Predicting an impact means calculating whether two objects traveling through space at enormous speeds will arrive at exactly the same place at exactly the same time. To measure that risk, astronomers rely on increasingly precise observations collected over months and sometimes years. Every new measurement reduces uncertainty, allowing computers to refine the asteroid's future path. In many cases, an object that initially appears threatening is eventually ruled out as its orbit becomes better understood. This is why newly discovered asteroids occasionally make headlines before quietly disappearing from the news as improved data removes the danger. For the rare objects that continue to warrant attention, scientists use internationally recognized risk assessment systems. One of the best known is the Torino scale, which combines an asteroid's impact probability with the amount of energy it would release if a collision occurred. Most known asteroids remain at the lowest levels of the scale, meaning they pose little or no immediate danger despite occasional alarming headlines. Another important tool is the Palermo Technical Impact Hazard Scale, used primarily by researchers to compare an asteroid's impact risk with a normal background risk of natural impacts over the same period. Together, these systems help scientists communicate genuine threats without causing unnecessary public alarm. But what happens when years of observations continue pointing toward Earth instead of away from it? At what point does careful monitoring become an international emergency, demanding action rather than observation? Chapter 3. Can humanity defend Earth? For thousands of years, humanity could only watch the sky with wonder, completely powerless against whatever the universe decided to send our way. An asteroid on a collision course would have been an unavoidable natural disaster, arriving without warning and beyond the reach of any civilization. Today, however, the situation is fundamentally different. For the first time in Earth's history, our species possesses both the knowledge to detect a potential impact and the technology to consider preventing one. But planetary defense is often misunderstood. Many imagine a desperate last-minute mission launching just days before impact, racing against the clock to destroy a giant asteroid. In reality, scientists aim to solve the problem long before such dramatic measures are ever needed. The greatest advantage humanity can have is not a more powerful spacecraft or a larger explosion. It is time. In the vastness of space, even the smallest change in an asteroid's speed can produce an enormous difference over years or decades. Alter its orbit by only a tiny fraction, and that slight deviation gradually grows until Earth and the asteroid arrive at completely different locations in space. Instead of a catastrophic collision, the object passes safely millions of kilometers away. This simple idea forms the foundation of every modern planetary defense strategy. The mission is not to destroy the asteroid. It is to ensure that when our planet reaches the point where an impact would have occurred, the asteroid is no longer there. But proving that this elegant concept could work required more than mathematical calculations. Humanity needed to test it against a real asteroid in space. In 2022, the world witnessed the first real demonstration of planetary defense. Rather than waiting for a dangerous asteroid to threaten Earth, NASA launched the Double Asteroid Redirection Test, better known as the DART mission. Its target was not a world-ending asteroid, but a small moonlet named Dimorphos, which orbits the larger asteroid Didymos. Because neither object posed any danger to Earth, they provided the perfect opportunity to test a deflection strategy under real conditions. The mission itself was remarkably straightforward in concept. A spacecraft, traveling at more than 22,000 kilometers per hour, deliberately collided with Dimorphos. The objective was not to destroy the asteroid, but to transfer momentum through impact, changing its orbit by an extremely small amount. Although the alteration measured only minutes in its orbital period, it was enough to prove that humanity could intentionally change the motion of a natural celestial body. The success of DART confirmed one of the most important principles in planetary defense. Preventing an impact does not require blowing an asteroid apart. Given enough warning time, even a tiny change in velocity can grow into a massive difference over millions of kilometers, allowing Earth and the asteroid to safely miss one another. Yet, DART also revealed an equally important lesson. The mission succeeded because scientists knew exactly where the asteroid was, understood its orbit in extraordinary detail, and had years to design, build, and launch the spacecraft. Without that precious time, even the most advanced technology would have little chance of preventing a collision. If humanity's greatest weapon is time, what happens when that time begins to run out? Chapter 4. When time begins to run out. Every planetary defense strategy depends on one critical assumption. The asteroid is discovered early, but the universe offers no such guarantee. Not every object approaching Earth is found decades in advance. Some remain hidden until they emerge from the darkness, leaving scientists with months, weeks, or in the worst cases, only days to respond. One of the greatest challenges lies in the way we search the sky. Ground-based telescopes can only observe the night side of Earth. If an asteroid approaches from the direction of the sun, its faint reflected light is overwhelmed by intense solar glare, making it virtually invisible until it moves into a more favorable viewing angle. This blind spot has long been recognized as one of the greatest limitations of asteroid detection. History has shown how easily smaller objects can evade our surveys. In February 2013, an asteroid roughly 20 meters across entered Earth's atmosphere over the Russian city of Chelyabinsk without being detected beforehand. The object exploded high above the ground with the energy of hundreds of thousands of tons of TNT. Although no impact crater was formed, the powerful shockwave shattered windows across the city and injured more than 1,500 people, reminding the world that even relatively small asteroids can cause significant damage. For larger asteroids, the consequences would be far more severe. Every month of warning that is lost removes possible response options. A mission that could have gently altered an asteroid's orbit years earlier may become impossible if the object is discovered too late. At that point, humanity is no longer choosing the best solution. It is choosing from the few options that remain. So if prevention is no longer possible, how does the world prepare for an impact that cannot be avoided? If an asteroid is discovered too late to safely change its course, the mission shifts from planetary defense to disaster management. At this stage, scientists can no longer focus solely on preventing an impact. Their attention turns to answering a different set of urgent questions. Where will it strike? How much energy will it release? And which communities must prepare first? The answers depend on the asteroid size, speed, composition, and impact location. A relatively small object may explode high in the atmosphere, producing a powerful airburst capable of damaging buildings across a wide region. Larger asteroids can survive their descent, striking the surface with tremendous force and creating devastating shockwaves, intense heat, and powerful seismic vibrations. If the impact occurs in the ocean, it may also generate tsunamis capable of threatening distant coastlines. In such a scenario, governments and emergency agencies would rely on continually updated orbital calculations to identify the most likely impact corridor. As additional observations improve the asteroid's predicted path, evacuation plans could be refined, critical infrastructure protected, and emergency resources positioned where they are needed most. Every extra hour of accurate information could save thousands of lives. Fortunately, events on this scale are extremely rare. The vast majority of known asteroids pose no danger to Earth, and modern sky surveys continue to discover new objects every year, steadily improving our understanding of the solar system. Yet the possibility can never be reduced to absolute zero. That is why planetary defense is not built on fear, but on preparation, international cooperation, and constant scientific observation. Because if the day ever comes when a dangerous asteroid is truly heading for Earth, humanity's greatest advantage will not be luck. It will be everything we chose to do long before that day arrived. Chapter 5: The Asteroid That Changed Earth Forever. For most of Earth's history, asteroid impacts have been relatively small, leaving behind craters that gradually disappear beneath erosion, volcanic activity, and the movement of tectonic plates. Yet around 66 million years ago, Earth experienced an impact unlike any in recent geological history, an event that would permanently alter the future of life on our planet. An asteroid estimated to be about 10 kilometers or 6 miles in diameter slammed into the region that is now the Yucatan Peninsula at a speed of roughly 20 kilometers per second. The collision released an unimaginable amount of energy, equivalent to billions of nuclear bombs exploding almost simultaneously. Within seconds, a colossal crater nearly 180 kilometers wide was excavated, while the surrounding landscape was instantly vaporized by the tremendous heat and pressure generated at the moment of impact. The consequences extended far beyond the impact site. Powerful earthquakes shook the planet. Enormous tsunamis raced across ancient oceans, and vast quantities of molten rock, dust, and sulfur-rich material were blasted high into the atmosphere. As this debris spread around the globe, it blocked a significant portion of the sunlight reaching Earth's surface. Temperatures dropped, photosynthesis slowed dramatically, and food chains that had remained stable for millions of years began to collapse. Many species were unable to survive these rapidly changing conditions. Among the most famous victims were the non-avian dinosaurs, which had dominated Earth's ecosystems for more than 160 million years. Although countless organisms disappeared, some life endured, including the ancestors of modern birds and mammals. The aftermath of this single impact reshaped Earth's biological history, opening the door for new forms of life to evolve and eventually dominate the planet. For many years, scientists debated what could have caused such a sudden and widespread extinction. Some proposed massive volcanic eruptions, while others suggested gradual changes in Earth's climate. The mystery remained unsolved until evidence from around the world began pointing toward a single catastrophic event. In the late 20th century, researchers discovered an unusually thin layer of clay preserved in rocks dating to approximately 66 million years ago. This layer contained an exceptionally high concentration of iridium, a rare element that is uncommon in Earth's crust but relatively abundant in asteroids. The same boundary also revealed shocked quartz, minerals deformed by immense pressure, and tiny glassy droplets known as tektites, formed when rock was melted and ejected during an enormous impact. The final piece of the puzzle came from beneath Mexico's Yucatan Peninsula, where geophysical surveys revealed the buried remains of the Chicxulub crater. Measuring nearly 180 kilometers across and matching the age of the extinction, it provided compelling evidence that a massive asteroid had struck Earth at exactly the right time to explain the global catastrophe. Today, the Chicxulub impact is regarded as one of the strongest examples of scientific investigation in action. By combining geology, chemistry, physics, and satellite observations, researchers reconstructed an event that occurred 66 million years ago with remarkable confidence. The discovery transformed our understanding of Earth's history and also raised an important question. If a large asteroid changed our planet once, could it happen again? That question now drives modern efforts to detect, track, and study near-Earth asteroids before they become a threat. If you enjoyed this journey through the world of asteroids, consider supporting the channel by liking this video, subscribing, and sharing it with others who are fascinated by science and space exploration. Your support helps us continue creating documentaries that explore the wonders of our universe. Thank you for watching,